Hello, this is video 44. We have just been talking about conservation of energy. In this video, I'm just going to go over two more examples. So the first one here, I called it box sliding down the incline again. This is because we've done this exact same example in video 40. This was example number 2. But we did it using the work energy theorem, and now we can do the same example using conservation of energy. So this was a box that was sliding down a frictionless incline, and there was an angle of 30 degrees here with the horizontal, and then the box was starting from rest. What was the speed after it slid 2.5 meters down the incline? So use conservation of energy this time. So this is where we're going to write out the equation, and after a while, instead of writing 1/2 mv squared plus mgy initial, etc. I'm not even going to write the spring term this time. We don't have a spring in this problem. But after a while, you can just write KE initial plus PEG initial equals KEF final plus PEF final. That way, then you can cross out the terms that are equal to 0 without spending a minute writing down every term explicitly. So, for example, if we say that this is our final point here, y final equals 0, then we know that the gravitational potential energy final is 0. So we can cross this out. But if we had just written PEG F instead of this, then that's faster to cross that out rather than this, right? So I'm saying that you can just write KE initial plus PEG initial equals KE final plus PEG final. You can just write this for your conservation of energy and cross out the terms that are equal to 0 here, just to save time if you don't want to write out each term explicitly. So what else is 0? Well, the box starting from rest, so that means V initial is 0. So we can cross out this because V initial is 0 here. So you can see there's only two terms left. The gravitational potential energy is being converted to kinetic energy. And we're looking for the final speed. So we're looking for VF. So the m's are going to cancel out again because they're in each term. So we know that VF, just like in the previous problem that we just did, we're going to multiply both sides by 2 here and then take the square root. So we're getting the same exact equation as last time for this problem. The only trick, so that you don't make a mistake, is don't stick 2.5 meters for your initial height. A height is always a vertical distance, so the initial height is from here to here. Right? That's your initial height. It's not the hypotenuse, it's the side that is opposite. You can assume that there's a triangle here. We're looking for the opposite side. That gives us the height. So y initial, opposite uses sine, is actually 2.5 sine of 30. So as long as you get the correct height to start with, then you can plug it in here, and we'll get the same thing that we got last time. So 2g y initial, and when you do 2.5 sine 30, you're going to get 1.25, sorry, 2 times 9.8 times 1.25, and you plug all that in, we're going to get the exact same thing that we got when we did this in video number 40. So if you notice there's no friction, you're losing height, gaining speed, or vice versa, use conservation of energy. It tends to be easier than using the work kinetic energy theorem. So let me do one more example here. A block dropped on a spring. So you look at this example here, and it has a block that is falling. So it's losing height, it's gaining speed, but then it compresses the spring, so you know that the spring is storing potential energy. So when you talk yourself through the problem like I just did, that tells you, okay, this looks like a conservation of energy problem. The block had potential energy here that was from gravity, and then it got converted to storing that spring potential energy in the spring. So I like to start by writing down the full equation. 1/2 mv initial squared plus, actually, I'm going to write the full equation, but this time I'll just write the names of the energy. So initial kinetic energy plus initial gravitational energy plus initial spring energy, that's PES here. And for some reason, I prefer to use an I, it just looks better here. And then we have KE final plus PEG final plus PES final. So I prefer to write like this because it just takes too long if you write out every single term, because a lot of them will cancel to 0. So what's the point of writing it all out, right? So now we figure out what's equal to 0. Well, the lowest point that we care about is going to be right here, because we're given information about when the spring is compressed to its maximum here. And that's the lowest that it gets. So Y final equals 0 at this location. We don't care what happens at the ground. So if Y final is 0, that means it has no gravitational potential energy at the end, because it's mgy and that y is 0. And then let me start from the beginning here. So it's dropped from rest. You have to assume it's dropped from rest. That means V initial equals 0. That means there's no kinetic energy initial, because that's 1/2 mv squared. It definitely does have some initial height. So it definitely has some gravitational potential energy from here to here. That's the initial height from here to here. And we can figure out what it is because it's dropped from a height of 60 centimeters above the top. This is why it's extremely important to draw pictures, because you're going to be tempted to just use 0.6 meters, that's your 60 centimeters. You're going to be tempted to use that as your initial height. But that's not the initial height, because the initial height is relative to this place here at the bottom, and this was 0.3 meters, the compression of the spring. So hopefully you can see that the initial height is actually these two heights added together is 0.9 meters. Right? It's the height from the 0 point up to here. And initially, is there any spring potential energy? Well, this is the initial condition on the left here. The spring is not compressed or stretched. It's in its equilibrium position. There's no spring potential energy. So the process that I'm going through here is exactly what you want to do. Just go through each term and see what's equal to 0. Is the final kinetic energy 0? So over here, is the object still moving? So this is kind of a key thing that you have to realize. It says it's the maximum compression of the spring at this location. When something is compressed to the max, it means it cannot compress any further. That means the object must stop. It's just like when you throw a ball and it reaches its maximum height, well, then it stops at the max before it goes down. So at the maximum compression, the object will stop. So it turns out there is no kinetic energy at the final condition either. But there is spring potential energy because there is some compression of the spring. But we're just ending up with two terms. mgy initial for the initial gravitational potential energy, and then the final spring potential energy, 1/2 kx final squared. So it turns out in the problems that we do, you're usually left with 2 or 3 terms, even though you start with 6. It's possible to end up with 4 terms, but usually it's going to be 2 or 3, just the way the problems are written. So now, notice that you cannot cancel out the mass because it's not in both terms, but we're looking for k here. So we can solve for k, multiply both sides by 2 to get rid of that 1/2, and divide by x final squared to get the k by itself. Plug in the numbers. We're going to have 2 times 9.8 times 0.9, that was our initial height over here. X final is the compression of the spring, which is always measured relative to the equilibrium position. So it's 0.3, that's how much the spring is compressed. So 0.3 squared. So plug all of those numbers in, which I did, and I got 98. And if you remember, the unit for the spring constant was Newton per meter. So those are all my examples right now for conservation of energy, but we're going to do some more where we're going to be adding friction. We're still going to be following the same exact steps. So just to recap the steps, Very quickly, write down the conservation of energy equation, cross out the terms equal to 0, and solve for your unknown.